everyone. My name is Tom Pingle. It's my pleasure to be the moderator for this session. We are in session 6, Power of Maps for Equity and Social Justice. We've got 4 presenters today. Each presentation has about 20 minutes total allocated to it, about 15 minutes for the presentation and a few minutes after for questions. So with that, I'd like to introduce the first speaker. This is Gunjan Barua. If you want to come on down, turn it right over.
Hello. All those who are present here in person and those who are attending online, I welcome you to my presentation today. My name is Gunjan Barua. I'm a graduate student at Department of Geography at Virginia Tech. So today I'm going to be presenting about understanding perception of different urban thermal model visualizations. So let's get the presentation started. So first I'm going to talk about urban heat island effects. So urban heat island effect is the increase of temperature in the urban areas compared to the surrounding areas. In recent years, we have seen like extreme heat wave events across the US and where we have seen the urban residents were suffering the most. We have, from different literature and statistics, we have seen that the average temperature of the cities is projected to increase 2 degrees Celsius above that of a global temperature increase, and that might expose 2.3 billion people to extreme heat waves. It is also the #1 weather-related cause of death averaged over the past several decades. So how we are measuring the urban heat island effect? So mostly using satellite images like Landsat and MODIS. So why do we need to map urban heat island effect to contribute to equity and social justice? So we have seen that heat exposure disproportionately impacts marginalized communities, and the problem of heat in neighborhoods and the social justice aspects of heat distribution may not be immediately understandable to the residents. There is a gap in terms of data availability and how this information can be incorporated to respond to heat threats. This gap in extreme heat impact understanding is preventing the urban planners and residents to translate the scientific knowledge of urban heat to reduce its impacts. So we need to make sure that maps are displaying such information that is accessible and comprehensible as much as possible. And this might lead to increased engagement that can help achieve a better decision-making process for community-resilient heat planning. So how we can improve the estimate of urban heat island effect? So we have seen one example from Urban Heat Island Mapping Campaign, where they adopted an approach where volunteers were outfitted with small instrument mounted on a vehicle that collected the temperature from 5 to 6 feet above the ground. And with that collected temperature, later they applied random forest regression model to get an estimate for the whole city. We have also seen examples using ground-based thermography, where they were using thermal cameras and they installed it on top of buildings to get a thermal model of a certain area of a city. In recent times, we have also seen drones equipped with thermal cameras to map the thermal models for different parts of a city. So now let's talk about how the urban heat island effect is visualized in academic literatures or in popular websites. So here you can see some examples of how the urban heat island effect is visualized. And in these examples, they have used satellite images as well as drone images. And in terms of color maps, you can see that they have used like one of them have used like red, yellow, green, a diverging color map or rainbow style color maps. In some popular websites, we have seen using different types of color maps to visualize the temperature information. Like we have here example of from weather.gov or from climate.gov. We can also see some examples from some popular websites that the general population usually use, like the websites or the apps like AccuWeather or Dark Sky, where they're using different types of color maps to interpret the temperature information to the general population. Now let's talk about resolution. And now let's talk about resolution. So why do we need to visualize the urban heat island effect in higher resolution? And as already mentioned, that we in recent times we have seen there is an increasing trend of using drones for visualizing urban heat island effects. Why do we use drone? Because it can collect high resolution data. It has shorter time intervals. They can change speed, direction, and altitude as needed. We can also construct 3D models using the structure from motion techniques. And improvements in spatial resolution of thermal imagery are making buildings, trees, and sidewalks directly visible in the scene. So talking about all these things, what we don't know about in this research area, we may not know how the color maps affect users' ability to quickly and accurately understand the thermal properties of a scene. We also don't know how the resolution from different image sources are affecting understanding of intra-urban thermal variability. We also don't know cartographic augmentations like shading affect how easily and well images are interpreted. Usually shading is used for visualizing elevation information, but can we use it for visualizing thermal data as well? Let's see. That led us to design an experiment where we had 66 participants and we gave them 3 map reading tasks. Our first task was the AB pairwise comparison task. So here you can see the map was provided and there was 2 points given. Based on the legend that was provided, they were asked which point has the higher temperature. The second task was a profile estimation task, where a line was drawn on top of the map, and 2 profiles were given. So based on the legend that was provided here, the users were asked to identify which profile matched the line that was drawn on the map. The third task was the map rotation task, where the users were asked to identify whether these are the same map, only perhaps rotated, or mirror images of each other, perhaps rotated. This map reading task is inspired by topographic map assessment task. So we had 3 independent variables. The first one was the color map, the second one was the source, and the third one was the shading enhancement. And we recorded response time and accuracy for this map reading tasks. And within the variables, we considered like the elements, those who have lower response time and higher accuracy are performing better than the others. So after the map reading task was conducted, we provided the users with a post-task questionnaire where we collected some basic information and asked for their preference for color maps and shading enhancement. The whole study was administered using PsychoPy. We analyzed the data with repeated measures ANOVA using JMP statistical software. So when we were looking into the response time of different tasks, we saw that there is a big variations within the response times because of the difficulty, because there were variations in the difficulty level of the tasks. So that resulted in variations in the response time. So to run the repeated measures ANOVA analysis, we log transformed the response time. And we also used least square means to see the variations within the variables. The whole study was approved by IRB before conducting it. So now let's talk about the data sources. So for the drone images, we use DJI Mavic 2 Enterprise Dual Drone, which has a thermal sensor and also has an RGB sensor. So we collected the data in Roanoke, Virginia during the summer of 2021. We used Pix4D structure from motion software to construct the thermal ortho image, a 3D point cloud, and a mesh of the surface. The output resolution for the image was 15 centimeters. We also used, for the satellite image, we used Landsat 8 analysis ready data for Atlanta, Georgia, and the nominal resolution for this data was 30 meters. For the color maps, one of our variables, we had 5 color maps. The first color map that we had was blue, white, red. The second one was Esri's temperature color map. The third one was Iron Bow, which is mainly used by FLIR. The fourth one is Viridis, which is a colorblind friendly color map. And the fifth one was Turbo, which is a more perceptually uniform version of jet. So now let's talk about the shading enhancement. So to apply the shading enhancement in drone images, we use digital surface model derived from the structure from motion reconstruction. So here you can see the drone image without the shading enhancement. And now you can see the image with shading enhancement. And as you can see here, in this way, the trees, cars, buildings, and other forms of land cover are more clearly standing out. We also use the similar technique for satellite images where we used LiDAR-derived DSM to apply the shading. Here you can see the satellite image without the shading, and this is the image with the shading enhancement. Now let's talk about the results that we got from our perception study. So first let's talk about the color map results. So as you can see here, we have our 5 color maps and how they performed in terms of response time and accuracy. So what we found out that the iron bow color map has the lowest response time and it also has the highest accuracy. In terms of ANOVA result analysis, we have also seen that both of these results are significant. So to summarize the color map results, we can say that the iron bow has the lowest response time and also it has the highest accuracy. We have also seen a surprising result for Esri Temp, where we saw that it stood second in terms of accuracy and it stood third in terms of response time. Now let's see how the sources have performed. So for the sources, we have seen that the drone images have lower response time and it also has the higher accuracy. But in terms of, according to the ANOVA analysis results, we have seen that the response time results are not significant. So we can summarize from these results that the judgments made from drone sourced images are more accurate. Now let's see how the shading enhancement have worked. So in terms of shading enhancement, we have seen that the unshaded images have lower response time. And we have also seen that the enhanced images, on the other hand, have higher accuracy. But from the results of ANOVA analysis, we can see that the accuracy results are not significant. So to summarize that, we can say that the unshaded images are faster to interact with. That brings us to the discussion of visual clutter, where visual clutter is the state where excess items or their representation in a visual lead to degradation of performance at some tasks. So we measure visual clutter with subband entropy, which is related to the number of beats needed for subband image coding. So as you can see from the graph, we have calculated the subband entropy score for the 5 color maps, both for unshaded images and also for enhanced images. And as you can see here, all the enhanced images have higher subband entropy score. That means they are more cluttered. So when in general we are looking into looking into enhanced images, we found out that there are like more elements to interpret. That means they are more cluttered. As there are more elements, users are taking more time to interpret it, and this additional elements is also helping them to achieve a better accuracy in terms of decision making. We also looked into the shading interaction with different color maps and sources, and we have found out like 3 out of 5 color maps have better accuracy when the enhancement is applied. And these 3 color maps are Iron Bow, Esri Temp, and Viridis color maps. We have also seen that in terms of sources, that the enhancement is increasing accuracy for satellite images, but it's decreasing the accuracy for drone images. Now let's see what data we found out from our post-task questionnaire. So among our participants, 74% of them were graduate students, while 20% of them were undergraduate students. For the preference for the enhancement, we found out that 67% of the respondents are preferring the enhanced images compared to 33% who preferred the unshaded images. And for the ranks, we have seen that Turbo color map is the most preferred one, while Iron Bow color map is the second most preferred one, and Esri Temp is the least preferred one. So in conclusion, we can say that the performance matters, and so does preference. and people are more likely to be engaged with images they find preferable. For the color maps, we have seen that the color maps were significantly different in performance and preference. Ironbow, for example, was a strong performer, and it was also well-liked. EsriTemp, on the other hand, it was not well-liked, but it was a strong performer. And Viridis is a poor performer overall. For the DSM shading, we can say that it was well-liked, but the performance wasn't clear. Some of the performance difference may be attributable to the increased visual color. And for the source, it matters, as judgments made from drone-sourced images were faster and more accurate. So now addressing back to the need of this study, we need to make sure that urban heat island effect is visualized in such a way that it's easily accessible and comprehensible. That way, we can contribute towards ensuring equity and social justice by making heat-resilient communities. I want to thank Cages for giving me this wonderful opportunity to present here. And also thanks to my advisor, Dr. Thomas Pingle, for his wonderful mentoring. And thank you all for listening to me. Thanks.
Thanks very much, Gunjan. I think we have some time for questions, and I want to remind the folks that are online that they're welcome to submit questions as well, and we've got somebody monitoring the chat.
Got a question.
Sure.
One thing that I was struck by is that some of the preferences people have towards different colors. The preferences people have towards different colors might be things they're used to versus like better. I'm not sure when the EsriTemp like color scheme came out, but do you have any sense if any of those color schemes are newer and that you think maybe they'll become more preferred over time once people are used to seeing images with those colors? I don't know, have you thought about that generally for the different color maps used?
So we actually put significant amount of thought like which color maps to test. So in that case, like we found like the turbo color maps or the rainbow style color maps are the most popular ones, because like when I received the participants, there were like people from different disciplines who were also working with temperature data, and they were using mostly turbo color maps for that. So they were more comfortable seeing that, but in terms of the results, we haven't seen the reflections of their preference in terms of their performance. But the thing you mentioned that we didn't consider like which color map like came to in use at what time. But like the 5 color maps that you are seeing here, these are the most popular ones that are being used for color map for temperature data visualization. So, yeah.
Very interesting presentation. Maybe I did not pay attention correctly, but your participants were students, or they were like people who work with? Yeah. Are there people who work with the temperature data? Have you tested that, like what participants are?
So the data was collected during the summer of this year, and it was kind of like an open circular kind of thing. But so we didn't have any preference like whether someone has to be a student or not a student. But like there was an option like to indicate their education level, and this was the result that we found out. So but we also had like someone who were not students, and when I was interacting with them, like not many of them uses like temperature data to work with.
So you did not ask participants if they are experienced users of such maps?
We do have, did ask them their experience level with geography, but we did not ask them whether they have experience working with the temperature data.
Did you find any significance?
No, we actually ran the correlation between like whether their experience level was somehow correlated with their accuracy and response time, but the correlation was like very insignificant. So that's why we didn't mention it here.
Okay, thank you very much.
Thank you.
I wonder if there's time for one question from online.
Yes, go ahead.
Yeah, please go ahead.
Oh, thanks. This may be, sorry, there's a bit of feedback. This may be of relevance um, to the last question. I turn my camera off there. If you can still hear me.
Yeah, sure.
Great. So I'm wondering if you had considered these participants across cultures as maybe another part of this study or a future part of this study, because it's often been the case, or it's been found that peoples from indigenous cultures really connect with remote sensing data and can interpret it very well. But maps are a very colonial construct, and it's just as we heard, yesterday, I think it's just not within that particular worldview. So it really matters as to who you're making the maps for and who the data is for, as to who is going to connect with it and be able to interpret it. So I wonder if maybe that could be something that you could think about in the future.
Yeah, that's a very good point that you mentioned here, and I can also say that in here, so when we were building the high resolution thermal models, and as already mentioned here, we overlaid the temperature information with the digital surface models for both drone data and satellite data. So there is another component that we haven't mentioned here, that's the 3D component. And when we were visualizing that 3D thermal models, we have seen that the elevation has a significant role in terms of visualizing, in terms of the urban heat island variability. So that's what we also want to test as well. So maybe when we are testing that, we can also include that cultural aspect as well, to see how people from different background people from different background are responding to the heat island information. So yeah, thank you for raising that. Thank you.